Hello, my name is Samuel Schlafer, and this is my Physics 2211 Lab 2 presentation on projectile motion. Little introduction to the lab. The purpose of this lab was to measure the position of a projectile affected by gravity and drag, both computationally and experimentally, and then compare the results. For my group, our object was a crumpled paper ball with a mass of around 2 grams or 0.002 kilograms. In order to construct the experimental model, I used the tracker app, and in order to construct the computational model, I used GlowScript code. Some of the principles behind this lab are force of drag being negative the force constant times magnitude of velocity squared times v hat, force of gravity just being negative mg in the y direction, and then the position and the velocity update formulas. Our lab procedure, we were required to capture a video of a projectile in motion. Then we had to import that video to Tracker, measure the object's position over time, and create an experimental model based off of those results. Then, using GlowScript, we created a computational model for the same object. The first time we ran through the code, we only accounted for gravity. The second time, we ran through the same model, but we also included a force of drag. Afterwards, we plotted the data generated by both models on the same graph and compared the results. Here are my experimental results. Here's a little analysis of the results. After looking at the first two data points, we compute that the initial position is 0.00623 in the x direction and 1.69 meters in the y direction. And we get the initial velocity of around 1.44 meters per second in the x direction and 0.394 meters per second in the y direction. Here was the GlowScript code I used to construct the computational results. As you can see, we input the mass of the ball as 2.002 kilograms. We inputted the position and the velocity vector we calculated from our experimental model. For deltat, my video was around 20 frames long, running at 30 frames per second, so it lasted 2/3 of a second, and each deltat was 1/20th. Then we calculated the net force as the force of gravity plus the force of drag, and included the momentum principle to update velocity and position over time. So here are some of the effects of the drag coefficient. I ran through the computational model with b equals 0, b equals 0.001, and then b equals 0.01. And as you can see, as drag constant increased, the graphs for position over time changed drastically, showing that it was traveling less distance over time. Here was the experimental versus the computational results. After looking at all three run-throughs of the computational model, the model that ran or compared the best with our actual experimental results was the model that had no drag, which just shows that our crumpled paper ball did not have very much drag. Some causes for deviation, outside forces, just overall friction, rounding error, and then human error from both placing trackers on the tracker app or throwing the object. Some additional questions. Do any of the models predict a terminal velocity? Yes, two models predict it. The computational model, when it's ran with drag, shows that after a certain amount of time, the magnitude of velocity stops increasing. The magnitude ends up increasing at around 1.4 meters per second. And then the second additional question, if the object were initially thrown straight up, would the time it takes the object to reach the ground remain the same, be longer, or be shorter? If the ball were to reach the same height, it would take the same amount of time to reach the ground, since that is entirely depending on the y component of velocity. But if not, it would be longer, because the formula to see how long something is in the air in projectile motion is 2 times v naught times sine theta divided by gravity, versus when it's thrown straight up, it's 2 v naught over gravity. So answer, shorter.